Well, I'd like to thank Olympia and the organizers for inviting me. It's really wonderful to come here. It's my first time in South America, and it's enjoying being in Buenos Aires. I'm going to talk today about the transition between the quantum level and the classical level, and think about the role of distinguishability and how that, in my journey through this, in my exploration of this topic, I began to conclude that distinguishability was an important factor. However, not in the way that I had originally thought. I had sort of thought that, oh, you know, as we're all taught, that the ability to label classical systems so that their permutations were distinct was the key to classicality. And so imagine my horror when I came across Nick Huggett's work, and he persuaded me that that was actually wrong. It took me a while to really believe him, but in fact, it's really not apparently true that the issue of being able to label permutations is such an important, crucial distinction. So I'm going to go through that, and the second bullet here is looking a little bit more into separability, and seeing the role that that plays in the quantum versus classical divide. And then further considering that question about what is it that allows separability to serve as a form of distinguishability for these and I'm going to call them quasi-classical systems, because once I completed this sort of journey, I began to conclude that classicality is really kind of a quasi thing, that there's never sort of a fully classical world, if you will. So that's maybe a controversial claim, but we can think about that more. So just a few preliminaries, as we've already seen with Decio's talk and so on, that actually, as Stephen French pointed out, there's two different considerations here. The question of individuality, whether certain entities can truly be considered individuals, is primarily a metaphysical issue. And the issue of distinguishability is primarily an epistemological issue. It pertains to what we can distinguish and our knowledge about things. So I just want to make, I think that's an important distinction to make. However, distinguishability does have a bearing on ontological questions, such as what is an individual? Are there any true individuals? It's certainly brought to bear on Leibniz's identity of indiscernibles, the idea that if there's no way that we can distinguish between two things, then they are the same thing. So, but I'm not going to enter into that metaphysical debate. I don't really consider myself qualified to make any kind of pronouncement on that, although I have some opinions and I'm leaning a certain direction. So I'm not going to take any hard stand on that and really consider that issue. But I'm going to focus more on the epistemological issue of distinguishability and see what we can learn about what that might imply for the ontological features that can underlie this distinction between quantum and classical. So I'm going to go through this fairly quickly. I have kind of a lot of slides, and you know, I'm going to perhaps not spend as much time on each slide as would be warranted ideally, but we can always go back and discuss. So the first thing I was going to do is review Huggett's finding that the non-relevance of this wonderful word, hexietism, which I'm going to avoid saying for the rest of the talk, for the classical quantum divide, and concluding that H-ism is really not relevant for the distinction. So this is what was very surprising to me. So let's just go back and review what that is. Lewis was the one who first used this term, as my understanding. If two worlds differ in what they represent de re concerning some individual, but do not differ qualitatively in any way, I shall consider that a hexaetistic difference. But even its formulation is controversial when you start to read about this, whether to define it in terms of the Lewisian possible worlds, which brings with it certain ontologies we may not want to adopt. However, the basic essence of H-ism is that an individual's identity transcends all its qualitative features. And then the opposite view, anti-H-ism, consists in saying that an individual's identity is constituted by its qualitative features and nothing more. So let's see how this is usually brought into the picture with regard to classical versus quantum entities. The idea is that if you have H-ism, then interchanging two qualitatively identical objects occupying two different states does constitute two different configurations. So we've got these two coins with their identities, Fred and Joe, and you know, they can, and there's a different configuration for each one having, you know, these different states. Okay, so so in this case, the label represents a form of individuality that serves to distinguish the two coins. And so this is how, and I'm sure you all know this, so I'm just going to go through rather quickly, that this is often seen as the essential distinction between classical and quantum systems. So, you know, we have these 4 different configurations here because we have to count the different permutations for Fred and Joe. But when we have a pair of quantum coins, then the state in which they are in different states, the configuration in which they are in different states, there's just one instance of that. We don't count permutations. So that's usually seen as the key distinction. So the way to formalize this, as Huggett points out, is that the phase space description, gamma space, if we call it that, specifies which component system is in which state. So it presupposes this kind of H-ism, that they can be labeled. And here's an example that we have the position of coin 1, position of coin, you know, or object 2, position, momentum, and so on of the two different systems. On the other hand, the distribution space description, which Huggett calls Z space, simply specifies only the occupancy number of each of the states. Just tells you how many degrees of freedom are in each of those states. So the example would be you have one particle with momentum p and 2 particles with momentum p prime. So if we call each object state its mu space, it just looks like this. It can be in either the head state or the tail state. And their gamma space, their combined composite phase space, is this space here where we have Joe's possible states, Fred's possible states. So they have these 4 possible states. However, here's the crucial step. If, as Huggett points out, if classical objects, or if we can correctly think of them as never being able to occupy the same space-time location, then we immediately lose 2 of the possible forms of occupancy. They can't both be heads, they can't both be tails. So the phase space becomes smaller. And then we find that if we look at the frequencies of the possible Z space distributions, then there's no empirical difference between those 2 formulations. So that in the classical analogy, if we've got coins, and of course you can have a more realistic system, but it turns out to be the same, where you're losing states with joint occupancy, with occupancy more than 1 degree of freedom in that state. And so here we have the 2 possible remaining states, one in each, 1 heads, 1 tails. We have 2 configurations corresponding to that. So the frequency of that distribution is 2 over 2 or 1. But then in just simply the occupancy representation, we have 1 instance of that, and it only happens 1 time. So the frequency is again 1. So the surprising result is that for any given distribution, it doesn't make any difference whether you represent this in phase space, which supports hexaetism for the objects, or distribution space, which doesn't. You hearing anything? Okay. Getting some noise. Okay. So there's no empirical difference between these 2 representations, and so we can't say, well, you need gamma space to describe the classical systems, and that's why they must be hexaetistic. So this is a conclusion, and while it is somewhat bewildering for our intuitions about the difference between classical and quantum objects, we actually need this result. And why do we need it? Because of the correspondence principle. The classical Maxwell-Boltzman distribution must and does emerge as a limit from the quantum statistics. So we're going to look at that now. That's what we're going to transition to now. And the Maxwell-Boltzman statistics are often said to be the dilute low occupancy limit of both the quantum statistics. But this does need to be made more precise, since no 2 fermions are ever in the same state either. So we'll look at that in what follows. So this is just a recap, which I think you already get the idea here. And the puzzle is then, In what sense, in view of the fact that we need to be able to get the classical distribution out of the quantum distributions, and we do get that, this presents a challenge for the idea that classical systems have a sort of digital on-off individuality that quantum systems don't. There has to be some sense in which the classical nature of the objects emerges in a continuous way. So that's kind of the puzzling finding here. So this is a journey that I went on now to try to make sense of this. Well, I said, let's look at the statistics. Just a quick review of what they look like. Maxwell-Boltzman statistics here. The basic distribution with the normalization, depending on the number of particles in the gas. And then the Bose-Einstein distribution looks like this, where mu now is the chemical potential. We'll talk more about that later. The Fermi-Dirac case, which just differs by a plus sign. So one observation, if you go back and look at the advent of quantum theory and Planck's struggle with blackbody radiation, is that they had a classical wave distribution already, which, as everyone knows, didn't work. It worked for one limit, for the long wavelength limit, low energy limit, but not for the higher wavelengths, the ultraviolet catastrophe. So this is a classical wave distribution. The classical particle distribution was already well known. And what happened was that it was discovered that the quantum distributions really have to interpolate between these two extremes of a wave and a particle sort of distribution. And here's just an example of how that falls out of the Bose-Einstein. The Planck distribution for electromagnetic radiation looks like this. And as we see for small energies compared to KT, we just expand the exponential to first order. We get rid of the ones go away, and we end up with the Rayleigh-Jeans law for classical waves. So that works for the small energy limit. Then for the larger energy limit, we clearly have the exponential term swamping the unity term, and we end up with the particle-like Boltzmann distribution. So this is just kind of a nice way to remind ourselves that the quantum distribution smoothly goes to the wave-like classical distribution in the small energy limit and the particle-like classical distribution in the high energy limit. So let's now look into the assumptions that go into deriving the various distributions to try to get clues as to what might be the key differences. So the first thing to notice is that the Maxwell-Boltzmann distribution, and we'll look at more detail in what follows, just takes the partition function, which is the normalization factor for the probabilities, as the direct product of n individual partition functions. So clearly, right away, it's implying a kind of statistical independence, a separability. And the key point, if you want to stop paying attention now, this is where you just take, this is the take home. You cannot do that if you want to get the quantum statistics. So we're going to just look in more detail as to how that works. So this, I guess, is a little bit technical. I had to go through, I found some lecture notes from someone who declined to say who they were. So I just went through this, and if someone wants to track this down, I'd be happy to work with you on it. But this is just a typical basic derivation of the different kinds of statistics in its most general form. And what you do is you first look at the possible energy states of a single degree of freedom, and in saying particle, I don't want to imply that it's a localized corpuscle or anything like that. But generally, it does follow the exponential dependence, which we'll look at later. We look at the number of particles that could be in that given state, which is nr. We look at the possible energy states of the entire gas with n degrees of freedom. And basically, you're just adding up however many particles are in each energy state to get the total energy for that particular state over that particular distribution, and noting that the total number of degrees of freedom is just the sum of all these different possible occupation numbers. And here it's just good to note that this is just a distribution. Okay, so we're not working with any kind of phase space or labeling or anything like that. Now the standard result is that the probability of this macroscopic total state R is proportional to, the beta is simply 1 over kT to the exponential minus beta of this energy ER. And then we get the constant of proportionality as 1 over the partition function that looks like this. And again, this is the ER for the entire gas, so that's the partition function for the entire gas. So the probability that it's in the state R is simply given by this. Now, once we have this basic expression, it's perfectly general for all kinds of systems. We can get the average number of particles by taking the weighted probability for each of these occupation numbers as follows. We do some manipulations on it. This is what people like to do in statistical mechanics, get into a compact form where you're dealing with in this form. But it's a perfectly general result for the average occupation number of that level R. Okay, so we can use this whenever we find the partition function to get the occupation number. Okay, so let's go back now for just a single particle with possible energy states, single degree of freedom, energy states ER. This is what the probabilities look like, where this is just the single particle partition function. And now the key step here that I mentioned earlier is that for the total gas with n particles, you can get the average number, occupation number in the given energy level by just taking the partition function for a particular number of degrees of freedom as the direct product of all the individual degrees of freedom partition functions. So that once you do that, use this expression, then you just plug in your formula for the average occupation number, and you see you get the Maxwell-Boltzman distribution. Just to kind of highlight here that we're assuming that these are independent degrees of freedom, and we get the Maxwell-Boltzman distribution arising from that assumption. However, you cannot do this for quantum systems that have a constrained number of particles n. So this is the striking difference, that if we want to start dealing with bosons that have mass, photons are a different case, as we'll see later. But if they do have mass and you want to fix the number of particles, then right off the bat, you cannot do that. So to me, this is where I stopped and said, okay, this is important. Now, maybe some of you already know this, but this is an important feature that clearly tells us that there's something going on with the quantum systems of the quantum gas in which they clearly cannot be viewed as independent degrees of freedom. And of course, it's not a surprise to those of us who know about quantum correlations and so on, but quantitatively, it's expressed in this way, where what we end up having to do is incorporate the restriction to the number of particles through the chemical potential as a Lagrange multiplier. And so we're dealing with what's called the grand partition function, with z with a little caret over it. And you just get that by having an additional factor, beta mu n, that you then do your algebra, incorporate, take your common products and collect in terms of the occupation numbers in this manner, such that you end up subtracting mu from each of the individual energies like this. And you just re-express as a set of infinite sums. But note now that we are now taking the possible occupation numbers from 0 to infinity. So in doing this, we've lost our restriction to n for the moment, okay? We'll come back to that in a minute. So we just do some more manipulations here, noting that mu is always going to be less than each energy level. And with that, we can note that each of these factors is this kind of expression that we can re-express each of those as this 1 over 1 minus x. So we do that. We end up getting the grand partition function looking like this. And of course, we take logs of both sides, so we get this nice compact form. And then we can use this to apply that general formula that we obtained before. So before we do that, let's go back and remark about having lost track of our fixed number n. What we had to do, interestingly, in order to fix our n, is to go to a representation in which n is in principle allowed to vary, because the grand partition function is, the grand canonical ensemble is that ensemble in which your system is taken as being in contact not only with a temperature reservoir, but a particle reservoir, so that it can exchange particles. So kind of a surprising discovery that even for a system that you've already said is, you're taking it to be an isolated system with fixed particle number, in order to get the quantum statistics, you're going to have to go to this grand partition function. So in order to be able to fix your n, and what n ends up being is simply the average number for the grand partition function, which you can then recover by getting that as the sum over the average occupation numbers. So as before, when we go to get each of our occupation numbers, as we did before by using this formula, when we do that, we get the Bose-Einstein distribution. So the surprising thing is that we had to go to an awful lot of work because we were not allowed to express the partition function as simply independent degrees of freedom multiplying each other. Okay, so similarly for Fermi-Dirac particles or fermions, I'm not going to go through that, but the same basic problem comes up where instead of taking it as a direct product of all the probabilities, you can't do that, and you have to incorporate the Pauli exclusion principle, and you have to use the grand canonical ensemble, and you end up again with your fixed n really being kind of an average n that you get this way. Okay, so here, summing up now, all three distributions, taking into account the chemical potential, which often isn't done with the classical Maxwell-Boltzman distribution, but it turns out that in the dilute limit that gives you the classical distribution, this factor of beta times the chemical potential really reduces to n, the number of particles, over the individual partition function. So it's this coefficient that we had before. So that the three distributions, when they're put side by side, just look like this. This is Maxwell-Boltzmann. And then the two quantum distributions just have the additional factor, the additional term of a 1. So that in the case of Maxwell-Boltzmann, we have the mu dependence, the chemical potential dependence, is separable in the distribution and ends up just being a numerical coefficient. But if you want to compare it in a more revealing way, you can put it in this form. However, the chemical potential is non-separable in the quantum distributions. So that's the big distinction here. That was what I learned from doing this little exploration. I guess I'm still doing not too bad with time. So looking at the crucial role of this chemical potential, which is this obscure quantity that I had to kind of do a lot of digging to try to get some sort of sense of what on earth is this quantity doing, because I had studied a little bit of statistical mechanics a long time ago, but no one ever explains to you what the chemical potential is, or at least not in a way that I ever really could make any kind of physical sense out of. So just kind of exploring that a little bit further, the significance is that the first observation is that we can't just use the canonical ensemble. We can't just say I have a system that's got a fixed number of particles. We have to implicitly somehow say, well, I have to allow that they're not fixed, but in fact, we know that it is fixed. So there's something kind of paradoxical going on here. So it turns out that if you recall that it does come in as a Lagrange multiplier, and of course for any of the ensembles, the canonical ensemble, you also have your energy, your temperature, and your energy coming in as a Lagrange multiplier. But in the case of the quantum systems, you have to still have this Lagrange multiplier that represents a kind of a constraint force that is present in the quantum case, even if there's no contact with an external particle reservoir. So for me, that was the physical content, that the quantum degrees of freedom are somehow imposing a constraint force on each other that is not present in the classical case. So going back then to the idea of distinguishability and the H-ism that I talked about earlier, this whole exploration kind of gives us a negative finding. We find that if you try to treat quantum objects as elements of these separable probability spaces, then you just simply cannot get the quantum statistics. So what I mean by negative finding is this doesn't demonstrate that classical objects have metaphysical individuality or that H-ism applies to them, but it seems to me that it does arguably demonstrate that quantum objects are not independent and separable, and therefore probably not individuals and certainly not H-istic. Now, this could be debated, but that it seems to be this sort of the superficially reasonable conclusion to draw from this. And moreover, the mutual constraint of the quantum system expressed by the chemical potential mu, even at t equals 0, I mean, this is in the absence of any thermal interactions, represents a physical correlation or interaction that is not present in the classical case. So I'm just sort of saying if we're talking about individuality, we require some form of separability in the sense that at least we can say which degree of freedom we're talking about. We have to be able to talk about which one we're considering for individuality, and it seems that we probably can't do that in the quantum case. Okay, so this third section, so what allows the separability that we've found so far, with, at least in the probabilistic sense, to serve as some kind of a quasi-classical distinguishability? We don't yet have particles. We don't yet have impenetrable gas, little hunks that we think of as classical particles. So are we going to get that back in any kind of sense? So let's see if we can get that back. So looking again at this dilute limit of the statistics that we see in this, comparing the different kinds of statistics here, we clearly get the Maxwell-Boltzman limit obtaining in the limit where the exponential is very large, this swamping the unit term. And this limit, this is very well known that I'm just kind of reviewing, it applies in cases of high temperature and or low particle density. However, when you look at this, you kind of look at what people say about it. I'm going to present a little critique of the usual criteria, and I don't know if you may not agree, but let's see how this goes. Okay, so the standard argument, what I think is a real hand-wavy argument, saying how we get localized gas particles out of this limit is that people look at, they want to define an uncertainty in momentum, and so they use this root mean square expression, and they say, well, the average momentum over n particles, where they're all in random motion, is assumed to be 0 because all the random motions average out to 0. So this goes away, our average momentum goes away. Meanwhile, they get the p squared average they use the equipartition theorem, which says that the average kinetic energy is p squared over 2m, 3 equals 3 halves kt, so that they get the average squared momentum being 3m kt. Spot from here. Okay, so okay, fine, I've got my delta p now, and that went away. I've got this as the square root of 3m kt, so they say. Then this is plugged into the uncertainty relation, okay, to get a value for the position uncertainty. Now, this is just, random motion, but this is what's done so that they get a so-called position uncertainty that looks like this, from plugging that into the uncertainty principle. So this is often called the thermal wavelength, even though it's clearly supposed to be a position uncertainty. So then they say that, okay, now let us consider the volume that the gas is in, the number of degrees of freedom, the number of molecules in the gas, and look at what that tells us about the average interparticle distance, d, which we can represent as v over n to the 1/3, getting this average interparticle distance. Clearly, they're still assuming that somehow these things are localized, and that the degree of localization is given by this position uncertainty that they tried to come up with. So that this is what the condition boils down to, that our position uncertainty is much less than the average interparticle distance. Okay, but of course, as I've already complained about, There's problems with this. It applies a classical, not a quantum uncertainty to momentum in two distinct ways. We're using the equipartition theorem to get a value for momentum squared, average. We're averaging over n systems assumed to be in random motion to get a vanishing value for the average momentum. So it seems that the resulting uncertainty is really only epistemic, not ontological. Moreover, the derivation of the equipartition theorem, which is used to obtain that momentum uncertainty, presupposes the classical Maxwell-Boltzman statistics. In addition, the derivation conflates a wavelength with a position uncertainty, and clearly they're not the same thing. If a system has a well-defined wavelength, then its position uncertainty is infinite. So what's happening here is this thermal wavelength is really being interpreted as the spread of a wave packet, when the states available to the systems making up the gas are not necessarily described by wave packets at all. They could be plane waves. Okay, so this is, I think this is garbage. So I don't know, maybe I'm being too harsh. Now let's look at but sometimes you don't see the root mean square expression. You see just people just saying, well, okay, let's look at a de Broglie wavelength. Let's say, oh, thermal wavelength, I get that just by taking the average momentum given by the equipartition theorem. And then I'm going to associate a de Broglie wavelength with that average momentum, and I'm just going to do that. But again, de Broglie wavelength has nothing to do with average momentum. It's a property of a well-defined momentum, and so on. So it would be great if we could just say classical degrees of freedom have no spatial overlap, as opposed to quantum, which may be true, but the derivation really doesn't seem to warrant that. So I'm going to stomp on the, I tried to find an image of a female, but they didn't have it. So we just stomp on that, we walk away. But it clearly seems to be not a valid line of argumentation, but then I saw, well, it works. I mean, it works. So why does it work? So I spent about a month, trying to figure out, okay, so why does this thing work? It seems to, if you look at the actual systems, you look up different kinds of components and different types of molecules, and they'll put in the de Broglie wavelength, this thermal wavelength, and it works. And I'm like, what's going on here? So something about this thing has to be capturing something legitimate about the transition. So I said, okay, let's look at KT. So let's just kind of reshuffle this a little bit and see what does it say about the energy at a given temperature. Well, I'm throwing away some of the just unity order numerical constants, and we get that it has to be bigger than this thing. Okay. But then, yay, to my delight, I found out that this really is just the Fermi energy. Okay, so this quantity on the right turns out to be the Fermi energy, which is the chemical potential for fermions at zero temperature. And again, just kind of to recap and put it in the official value here, if we neglect these constants like 3 and so on. This is the Fermi energy, the chemical potential for fermions at zero temperature. So, and it is well known that fermions, at least, behave classically when the thermal energy is well above the Fermi energy. So that redeemed then the limit that has been obtained from the thermal wavelength, even though clearly there's a lot wrong with it. So then let's look at that limit and say, okay, well, what happens in this limit? If we, again, take note of the fact that the chemical potential is just the amount by which the free energy, the Helmholtz free energy, changes when you add a particle to the system. And this is the Helmholtz free energy. It's the difference between the internal energy of the system and the temperature times the entropy of the system. So generally, in the classical limit, the chemical potential is very negative. It's large and negative. So the only way it could be that way is if entropy is created when we add a particle, because this is the only way we're going to get a negative mu. It's by this term being large compared to the internal energy of the system. So, and again, when you have, the higher your temperature, the greater this negative term is going to be. So the more negative your mu is going to be, the more you're going to be into the classical domain. And you're also going to have higher population of the higher energy levels, which is going to give you that limit, which we already saw just straightforwardly in a mathematical sense gives you the classical limit. So, and the same situation does apply to bosons, even though mu can never be positive in the case of bosons. However, with increasing T, it becomes more negative. So again, you get this limit. So the dilute limit, we can be more precise about it. Clearly, a dilute doesn't just mean you can't have more than one particle in an energy state, because that already applies to fermions. So the dilute limit really means this condition, which means that when you're adding, just go to the next slide, that I'm getting to the end here. So the more positive and less negative mu is, the more quantum-like a system becomes, because that means that when you're adding a particle, you're actually increasing the energy significantly, at least more than the effect of this term increasing the entropy at that temperature. So that the internal energy tends to increase significantly when you are adding a particle or a degree of freedom to a quantum gas. But in contrast, in the classical domain, the more negative your mu is, what's happening is that when you add a degree of freedom to your system, you're increasing the entropy a whole lot more than you're increasing the internal energy. So just kind of reviewing this, the significance is that you're adding a particle at the classical limit, you're increasing you've got a statistically independent sort of increase in your state space, and it's not affecting the internal energy much at all. Whereas in the quantum domain, that new degree of freedom has to find an energy level contingent on the pre-existing energy structure, so that it's increasing that total internal energy with minimal increase in the entropy, because it's fairly clear where that new degree of freedom is going to have to go, certainly in a Fermi system, in a fermion system. So it's not, once again, in the quantum system, it is not independent of the other degrees of freedom in the system. So that's just kind of reiterating this separability in the classical case. And now I'm going to say this separability amounts to a form of distinguishability. Since if you look at these individual partition functions, in principle, we could apply labels to them. And in fact, that's kind of where you get this apparent counting the permutations, is by thinking of each of these as having, zeta 1, zeta 2, zeta 3 for the different possible degrees of freedom, and multiplying them together and getting this collective state space. And we don't really need this impenetrability at all. We're only dealing with energy states. We're not really dealing with spatial location, but we're simply dealing with the fact that the degrees of freedom have this labelability to them. Now, so the question, come back to the question, do we get this sort of spatial separability at all? Can we think of we know that in a classical gas, it seems reasonable to think that molecules have a trajectory and that sort of thing. Well, you can say that at the high thermal energies, this enables the decoherence arguments, that the interaction with the environment, with photons and so on, you can get decoherence to come into play. Now, personally, I'm not a fan of decoherence as an explanation of space-time determinacy. I think that that's a circular approach. I have a paper that talks about why I think that's not satisfactory here. So that's where I talk about that. So I don't favor the decoherence approach. I think it's really inadequate. And I argue for a different approach in which we do have an actual non-unitary collapse that happens as a result of inelastic scattering that I do quantify in some published work, and I can refer you to that. So either way, though, at the high thermal energies, we have reasons to think that we get space-time localization. And if we do, we get at least an apparent determinacy of position over time. And we can think of these degrees of freedom as having unique space-time trajectories that can at least confer a label for that trajectory. We can at least, epistemologically keep track of where each degree of freedom started out and where it went and so on, and label it in that way, even if that's not a hexaetistic difference, perhaps. But at least that's a kind of a classical separability that we're used to thinking is applicable. Okay, so I'm just going to kind of conclude here and say that what I've already said before, that you can have that the quantum systems are really can often be plane wave solutions. They're not localized. Many bosons can occupy the same state, and so they're certainly non-separable in that way. And here I'm going to agree with Ladyman and Teller, who have suggested that we need Fock space as a more ontologically appropriate description of quantum systems that provides just the occupation number basis and does not have labels. The Hilbert space formalism seems to have surplus structure. And here's where I disagree, a part company with Huggett. He has an argument that I really find that doesn't really work. He says that Fock space could be seen as having surplus structure because it allows in principle for an unlimited amount of particles. But I think that's okay. I mean, I think that relativistically we have to accommodate the possibility of unlimited number of particles. So I think I don't really think that's a good argument. It's not surplus structure if it can be unlimited in real cases. In contrast, we never have the non-symmetrized quanta. So the surplus structure in Hilbert space is just never of any use for anything. So, okay, and on that note, I'm just reiterating everything I've said before. I think that's pretty clear. References there. And thank you so much for listening. Questions?
Comments?
Oh, thank you, Ruth. Thank you. I really like this talk.
Thank you.
I have a comment and a question.
Yeah.
One is, I think you're absolutely right that H-ism isn't the key to the distinction between classical and quantum. In that respect, a lot of the statistical mechanics textbooks are very misleading because a lot of them start with classical and go quantum, and they do the classical on phase space, which suggests H-ism,
Right.
and then introduce the permutations in the quantum stuff.
Right.
There are textbooks who do it right from the beginning, who use the classical reduced phase space, which is a quotient by permutations. An early one, I think, is Alice and Hearn from the 50s or something like that. So that's just grist for your mill.
That's good to know.
The question, though, is, can you go back? There's a slide where you were talking about a non-unitary picture. That one, yeah. So is the idea that you get unitary evolution between collisions, and then you have inelastic discussions,
Right. Yeah.
Is that enough to give us apparent trajectories for these things? Because if it's unitary between collisions for a dilute gas, there's going to be an awful lot of spreading, even for fairly heavy molecules, in the mean free time between collisions.
That's something that I'd have to look at quantitatively. I think that if you have the amount of thermal activity that goes with that limit, with the higher temperatures, I'm thinking that you are going to get a lot of. It's not so much it's not the collisions. It's simply the thermal interaction. So if you've got boson, if you've got photons going between these molecules, that's enough to do that work. That's what I talk about is the inelastic scattering of photons. So it's the thermal interactions that aren't necessarily physical contact of the molecules, but simply the transfer of photons between them.
Okay, thank you. That helps.
Photons.
Okay, thanks.
Yeah.
Michael?
Yes, I somehow got lost. So we have non-separability of the states in the sense that we have entangled states. This is a physical fact. So the evolution of two or several quantum systems is not independently of each other. Okay. So these I take to be physical facts. But how do we get from there that the systems are not individuals, that there's no spatial determinacy and things like that? They somehow got lost.
Okay. Well, now certainly to a Bohmian, then if you have a Bohmian ontology, then you're going to, in your ontology, you're going to have space-time determinacy at all times.
I want to have a solution to the measurement problem. I mean, I never started, in the Bohmian of late days, right, for certain reasons. So we need some additional premises.
Okay.
And the point is not whether you suppose a Bohmian ontology or not. The point simply is that from non-separability of states, as such, nothing follows about spatial separability, about determinacy or indeterminacy or individuality or non-individuality.
Yes, and again,
So
I'm not...
additional premises.
Right, and I'm not going to, I don't have any claim about metaphysical individuality here, but as far as getting any kind of determinacy, this isn't, I don't want to be here to be like, go for transactional interpretation, but if you want to, there's your answer. Okay, so I'm not going to be like, oh, here's the transactional lady. So I'm not going to advertise the transactional interpretation here, but there's your answer. I can refer you to my books, and that solves the measurement problem.
No,
and I'm not going to.
The transactional interpretation again is about the dynamics.
Okay, so let me just give you a reference. Yeah, let me just give you a reference. So if you look at this paper, so here's where I address how, go into specifics of how the non-unitary inelastic interactions can give you determinacy. Now, you may not like it, or you may not believe it or buy it, but this is the way. I know I don't have time to kind of explain it here, but in the transactional picture, as I've developed it into the relativistic domain, there are arguments, very quantitative arguments presented for how you would get space-time determinacy. Okay, so that's where I would point you to.
Jane, you had Thank you. I wanted to pick up on the issue that Wayne raised. What you said about that was very interesting. So my understanding is that if you look at the spreading of wave packets and you calculate the amount that the wave packet will spread in a gas, the wave packet of an individual molecule in a gas, you find that it's widely spread way before the mean free path length, right?
Okay. Yeah.
No, and what that effectively means is that, and I owe this to David Wallace, who explained this stuff to me, so I should just say that now. The reason why it's kind of okay to think of classical particles in a gas colliding is not because really the particles are like little localized wave packets bouncing off each other, but that they're like plane waves colliding, and it just works out that it's okay to think of them as billiard balls colliding, even though the right approximation is that they're plane waves colliding, bouncing off each other, however you want to say it. Now, what you said suggests that if there's sufficient temperature, then photons, thermal photons are going to somehow make those wave packets constantly localized enough for us to pretend that they're not like plane waves colliding, they're like localized particles colliding. Mm-hmm. But do you have have you calculated that? Are you sure about that? Because it strikes me that it would be a quantitative question whether, we know from those really subtle Zeilinger experiments that thermal photons can kind of effectively bring about localization. But I would have just thought it's going to be quite sensitive to the details, and so I just wanted to know how confident you are about that claim.
Yeah, absolutely, and I don't claim to have done that calculation. I think that's a really important point, and I think that's something that's the next step, and that's why I kind of just alluded. I said, can we recover spatial separability? I'm conjecturing. It's really just a conjecture at this point. I have argued in connection with my development of the transactional interpretation that that behaves in the same way as the decoherence arguments, that it gives you the same order of localization, but it's a good point that that's something that needs to be very carefully, quantitatively looked at. So
Yeah, I mean, because it may be that they're relatively localized, but still more like plane waves than particles.
Yeah, I mean, and again, I don't really think that we ever have a situation as in the idealized, impenetrable billiard ball picture. I think that there's always, that's why I called them quasi-classical earlier.
Yeah.
But that's a good point. Thank you.
Yeah, thank you.
Yeah.
Yes, if I understood okay your talk, you kind of suggest that in the quantum case there's some kind of strong correlation between the particles that does not allow them to consider them separately. But from a physical point of view, this cannot be considered as the usual interaction. Its exchange correlations are not interactions because there's no Hamiltonian involved, blah, blah. And it is certainly not entanglement either because symmetrization of the wave function does not imply entanglement necessarily.
Yes.
So the question is, do you have any suggestion or ontological explanation of where does this non-independence comes from? Because it's a very strange sort of non-independence, right? Exchange correlations, yes.
Yeah, no, great question. And this is the point that I left off in my exploration. So, to me, the significance was, whoa, we've got this chemical potential being very important and playing this crucial role, but what is it? Clearly, as you say, it's not an interaction described by any Hamiltonian, and so on. So I welcome anyone who would like to explore that. It's a wonderful question. It's very intriguing, but whatever it is, it's some kind of a capacity of the quantum systems to be aware of one another in a way that the classical degrees of freedom are not. And so, yes.
No, at a certain point, I think you say that the grand canonical partition function was essential. But maybe I missed something. But we have general theorems that say, in the classical and the quantum case, that there is equivalence of ensembles. I mean, it's just a question of practicality to use the canonical or the grand canonical. But you can do any computation in principle in the microcanonical, in the canonical, and the grand canonical. So I don't see why.
Yeah.
That's what I had three observations. This was first.
Yeah, again, and I don't pretend to be an authority in statistical mechanics at all. So I would yield to a superior authority in terms of the foundations of statistical mechanics. But what I found striking was that in order to get the Bose-Einstein, the quantum distributions, you seem to have to go to at least nominally a formulation that is usually used for the grand canonical ensemble, even though I agree, technically you're not in that situation. You're not dealing with a particle exchange situation. So that's something that I would welcome input on as to how to interpret that. But clearly you have to involve the chemical potential in this non-separable way.
Yeah,
so that's really my main point.
The second thing is that I think your thermal interaction will be sufficient to obtain what you, that's my intuition, will be sufficient. But you will get a localization of it in the decoherent side. I mean, from a foundational point of view, I will not be satisfied. As a Bohmian, I will use this technical result to say that the conditional wave function shrinks around the actual trajectory. And in another interpretation, you need something like that. But by itself, will not prove localization. The thermal idea will give some decoherence on the condition on the reduced density matrix, something like that, but no more than that.
Yes, for decoherence, that's what you would get. Yes, and again, that's not the way I would go. I would go with a genuine non-unitary collapse that localizes the degree of freedom. Okay. And that's in my references.
You will do that way, I will do it the other way, which is more or less equivalent.
Yeah.
And the third thing is that this is equilibrium, but going back to the main issue, philosophical issue of identity, distinguishability, what is really relevant there is non-equilibrium. I mean, equilibrium is not, we are not in equilibrium. There, the basic issue, I think, is identity and distinguishability in non-equilibrium situations, which is our world. I mean, if we want to go really to the classical regime, our world is clearly in non-equilibrium.
Yeah, I certainly think that there's a lot of work to be done there, but it seems to me at least that in order to get off the ground, you'd have to at least start with the equilibrium situation maybe to get some clues. So that's what I started with.